Welcome to this tutorial which illustrates how to simulate a water wheel in Ansys CFX. By the end of this tutorial you will be able to generate an unstructured mesh in ISAM CFD, set up a rotating mesh, set up multi-phase flow using the volume of fraction method, and also generate animations for transient simulations. As this is a moving mesh simulation, it is composed by two different domains. First, the rotating domain, and second, the stationary domain. We start with the rotating domain. We have already created the geometry in ISAM, so now we are just going to import it and then go to the next step, which is mesh. So this is the geometry. This is the rotating wheel enclosed in a circular domain. I have divided the surfaces into different parts. Now you can only see the walls, which is the water wheel, and this is surrounded by an interface which is shown now, and this interface is pretty much the connection between the rotating and the non-moving domain. The interior surface here is for initializing the water level. Of course there are other ways to do it, for example by using the volume of fraction. And we have two different volumetric parts, one for water and one for air. Now we simply click on mesh and we define the global mesh size, which is the size of the largest element on the domain. Then we define the size for each part separately. If you want the same size for all of them, you can simply click on maximum size and insert a number. Otherwise you have to define the number one by one for each part. If you have no idea what numbers to put in, you can start with a large number and then start decreasing. You have different options here, such as defining the mesh size on the surface, or defining high density regions of mesh. And then the last step is to compute the volume mesh. For this tutorial we're using a coarse mesh, and now we are waiting for the mesh to be generated, and we can only see the surface mesh. Now the mesh is still generated, and now it's done. So this is only the surface mesh, and if we take a closer look, we can see that it defines the geometry successfully. You can also check the number of elements. And if you want a better look, a closer look to the mesh, you can activate the solid and wire option. There is one way to see the volumetric mass. So this region, the water region, has been deactivated now. So you can see what the water level is. And based on these parts and volumetric, both volumetric and surface parts, the boundary conditions will be defined. Last thing is to check the quality of the mass by using the orthogonal quality criterion. If it's more than 0.3, it's enough for having a stable simulation without divergence. Of course, considering that your boundary conditions and initial conditions also make sense. And of course, in ISM you can also change the background color to give you a better view of your mass. Now the last step is to select the solver and then write the output files. We save the project first. The solver is CFX, and then we write the files which later will be used for importing them into CFX. We close this window. We just finished massing the rotating mass, and now we go to the remaining domain, which is non-moving, which is stationary. We double click. Again, we import the geometry. So the mass that you saw before will be imported inside this circular hole here. The size of the domain has been created only for illustration reasons, so you might find in reality that this size is not enough for analyzing this problem, and you would need a larger domain and also finer mass. Again, you can see that we have created two volumetric parts, one for air and one for water. We define the global size again, similar to what we did before, and the size for each part has been defined. In the areas where we left 0, in the parts which are 0, that means that this part takes the size of the global elements. we can see the surface mesh again. And the pink surface is the interface between the two domains. So for both the rotating and the stationary domain, we need to have a surface on each domain, which is the interface. And then once we import it twice to CFX, it will generate automatically one surface from these two. Now you can see that the quality is adequate, and we can write the output files for Ansys CFX. Now this is done, we can close the window. Now the next step is to import both domains in Ansys CFX. We can give a name to the project and then double click on setup to open the pre-CFX window. Now we import the mesh from ISOM-CFD. We start with the rotating domain. And we can define some main parameters of the problem. It's a transient simulation, so the total time will be 4 seconds in time steps of 0.06. We need to click in total time and then click apply. Okay. And now we can split the domain into two parts, one for the initial water domain and then for the air domain. So this part of the domain will be composed by air, this initial condition as with the movement of the wheel that will change. We can define some parameters of the working fluids. And then the movement of the domain. For rotational motion, Ansys CFX has an option for you to choose. However, if you want to choose linear motion, you need to import it as a CEL expression. So in the domain initialization, this is the point that we're going to define the water level. So this part of the domain will be composed only by air. So in the volume fraction, air will be 1 and water will be 0. the remaining domain will be renamed to moving water, and then we set the parameters for this one. The working fluid is water, and the density of the water is 19,997, and again rotating with the same speed as the previous domain. Around the z-axis. Everything is the same, and again we need to initialize the domain. The velocity and pressure values will be the same as before, and what is going to change here is the volume fraction for air and water. This domain is composed only by water, and therefore the value for air will be 0 and the value for water will be 1. We need to define the boundary conditions for the domain. First, starting with the walls, and the wall, of course, is the wheel. So we select the appropriate parts. And of course, the other boundary condition is the opening on the sides of the domain, which are going to have a specified pressure. And we need to specify the volume fraction again. We define the walls here again, and then the opening part. Now we need to import the stationary domain, and now you will see how these two domains combine and how they look like together. That gives you a better idea of the problem. And similarly to what we did before, we can divide the domain into the stationary air and stationary water domains. We select the volumetric part and the working fluid. However, this time the domain is not rotating, so it's not moving. Same models as before. And we initialize it with only air in this part and 0 water. The remaining domain is the stationary water domain. Which is not moving, and of course we use the same models as in the other domains, and it is composed by 0 air and 100% water. However, as mentioned before, this is just an initial condition and it will change based on the movement of the wheel. Now we need to define the interfaces. You can see some interfaces already being created here, and we need to define another one, which is the interface between the two domains. So first we selected the surfaces of the moving domain, and now the surfaces of the stationary domain. And these selected surfaces will be combined to make one interface, which is fluid to fluid interface, which means that we have fluid on both sides of the interface. We can start with a first order scheme for having stability and leaving the coefficient number, the number of iterations or loops, to 10 as default. You can see a warning here, which is for transient results. We can define transient results using the standard option. However, you can select the variables you want to record, and the frequency is every time step. If you have thousands of time steps, you can set that to a number which is more convenient for you, as these files take a lot of space. Now we can go to the solution and start the simulation. Usually moving mass simulations take more time. The simulation has not finished yet. However, we can stop it at any time and check the progress by viewing the results. So we can close this window and we can accept the solution as up to date and view the results. So this is the current position of the wheel at 7 iterations, 7 time steps. We can create a plane in the middle of the XY frame. And see how density varies in this plane. So the red part here is water and the blue part is air. For moving mass simulations, it's always very useful to have an animation. So now you can see an animation by using the calculated time steps. This is the beginning of the simulation and then proceeds. However, we haven't completed the simulation and we haven't calculated the solution in quite many time steps. So this is what we get after 7 simulations, 7 time steps. And of course we can show the variation of density along the z-axis. Animations are very useful in moving mass simulations. And of course we can make another contour of pressure, for example, on the water wheel. If we increase this number, it's going to give us a better visualization of the wall, and of course the color scale in our case would be very useful if we change it to inverse grayscale. And this is because we only have 2 numbers of densities. We only have the density of air and the density of the water. And similar to what we did before, we could generate an animation for the moving wheel in terms of pressure. We need to choose the time step option, and you can animate as many time steps as you want, and by defining the speed of the animation. And of course you can save this file into your computer.